Today we're going to talk about a fundamental machine learning algorithm, which is that of gradient descent. And what gradient descent's job is an algorithm that minimizes the MSE. Okay, so MSE is 1 over n times the sum as I goes from 1 to n of yi minus y hat I squared. Sorry about that. Okay, so it's just an average squared error. It's a way of saying how good or bad our model is. And what is our model? Well, let's say that our model in this circumstance is y hat is equal to beta naught plus beta 1 x. All right, so if this is our model, we can adjust beta naught and beta 1 to try and minimize this error. And what we saw before was that we had a formula for beta naught and beta 1. We had, okay, just set beta naught equal to this thing and beta 1 equal to this thing. And what that would do is if we had this graph for maybe both the parameters, if we had beta naught and we had one, I'll draw in the same color, if we had one for beta 1 as well, where these are functions of the MSE, so maybe the MSE looked something like this for beta naught. Maybe it looked something like this for beta 1. I don't know. Well, what we would do is just basically find the derivatives of this function, find the derivatives of this, and then set them all equal to 0. So what that would do is said, okay, well, I want this thing. I want this thing. And that means I want the value of beta naught that minimizes this error, which is this value. It's based off of the formula, which is derived from setting all of the derivatives equal to 0. Well, it turns out for many reasons that we don't do this, and I'm not going to explain too much as to why. It's not super important. But in general, the reason is that the complexity increases like crazy when we have more variables, different functions, and in linear regression, you could probably do this thing where you minimize this MSE by, this weird thing where it was beta is x transpose x inverse, that thing. Except even then, we don't really do that, even in linear regression, and definitely in anything more complicated, we end up not doing this. But we still have the same concept no matter where we go, of we have parameters which are values that we have to learn. And we're not going to forget calculus, okay? I did not teach all that calculus because just to do the linear regression thing, that I wouldn't do that. It is extremely essential for something called gradient descent, which you might guess because gradient is a calculus term. It means a vector of derivatives. Okay, so basically the intuition for it is that if these are our functions of the MSE, well, at any point we have, we're trying to figure out beta naught and beta 1. Maybe right now our beta naught value is this. Maybe it's 2, and maybe our beta 1 value is this. Okay, so this is called an iterative algorithm, where instead of just minimizing it all at once and doesn't matter what our values of beta naught, beta 1 were before, maybe we didn't even have any, we just all at once put them to the right value. We are not going to do that. What we're doing instead, and will forever do, is an iterative algorithm, which means we start at some starting point. Maybe we started here for beta naught, maybe we started here for beta 1, and then our goal is to iteratively go down and down on the MSE, and so we create some trajectory where we get to the bottom. And that's because we can't just solve to get to the bottom in later things. It's just too complicated. It's not going to work. So we have this general purpose algorithm, gradient descent, which really it says the following. And I'm going to do the next video, which is how it works for linear regression in particular. But for this one, I can give the intuition, which is basically that at any point, we have some starting point, beta naught and beta 1. Well, we can still get the derivative of the function, okay? It's not super difficult to actually get the derivative of the MSE with respect to beta naught and beta 1. It's difficult to get all of those functions and solve a system and set them equal to 0, and it just doesn't even really work. What we can do is still get the derivatives, and so I'm going to call them basically, I'll say m partial m by partial beta naught and partial m by partial beta 1. Okay, these are just functions, which again are something, technically it would be the function that looked like 2x or something like this, where it was maybe like that, except doesn't matter. We're not going to think about the entire function like on a graph. We're not going to think about it as like graphing the derivative. What we are going to think about it is a function where we can put in some values of beta naught or of beta 1. We shove it in that function and it returns a value to us, which the derivative is the slope at that point. What it says is if we're here, okay, the derivative at this point is something like this, okay? It's not this graph, it's the slope of this thing, okay? What I just drew here is the tangent, it's the slope of the ever increasing point here. Okay, so if I have this slope, maybe this thing is steep, maybe it's not, and maybe it's positive or maybe it's negative. So these are two very important qualities of this thing. Is here, this slope is positive. It means if I was to move beta naught to the right, the function would probably go up, or the MSE would probably go up. And if I was to move beta 1 to the right here, that means the MSE would probably go down. I didn't explicitly label these here, but I really should have. This is the MSE here. This is the MSE here. Okay, so we're trying to get the error to go down on these functions. And so what we're going to do is whatever our values currently are of beta naught and beta 1, maybe it's this, maybe it's this, and then we're going to get the derivatives. And so we know that function, we can derive that function. We shove in all the values so that we get this, the value of this slope here. That's the wrong color. So we get the value of this slope, and that says, okay, maybe it's positive 2. And what that says is, one, that it's positive. That means, again, if we go to the right, we're probably going to increase the function. There's a theory in calculus that says that is true, that if we move in an infinitely small direction of beta naught to the right, that means our MSE will increase. And here, if we move it infinitely small to the left here, if we increase or decrease beta naught by a tiny little amount, our MSE will definitely go down. Our error will go down. And so if we keep doing this, well, all we have to do is just move a tiny bit in the direction, the opposite direction of the derivative, really. Okay, so the derivative, you can think about it as a number that's saying, okay, if this is positive, well, then I actually want to go to the left, because that means I would be increasing. I don't want to increase, I want to decrease. So I'll move in the opposite direction of the derivative. I'll go to the left. And if it's the derivative's negative here, well, I want to go to the right. And so that is you can think about that as the negative direction of the derivative, because if the derivative is negative, then we'd want to go positive. If the derivative here is positive, we'd want to go negative. We always want to move in the opposite sign, or the direction that is away from it, because that is what minimizes the MSE iteratively. So we keep doing this until we get a trajectory, until we go down like this, and we hit what's called a local optimum. Okay, and so this is a huge problem if we had something like this, where our MSE was actually a function that looked like this, okay, and we had some starting point where we did this. Well, we'd actually go down and we'd end up here because we don't want to go back up. It's going to keep going down. And so it's not going to get the absolute minimum error. Of course, we would have preferred we hit this point rather than this one, except we didn't. It doesn't always work out that way. So I hope that made sense. And if you liked the video, please drop a like, and I'll see you in the next one.